This kind of problem you're going to see probably for sure on your free response section and your AP Calculus test this year. So let's talk about this. We have a beach and there's sand on the beach. They tell us, oh, the tiny thing that I left out, that last sentence should say at time t equals 0, the beach has 2,500 cubic yards of sand. So there's some sand on the beach at the beginning of the problem. Something happens to make some sand go away. So in this case, the tide is taking some of the sand away. And then there's something else making more sand come in. So in this case, we have a pumping station whose job is to add more sand to the beach. So we have the sand we started with. We have the tide taking sand away. We have the pumping station adding sand in. So we're going to get asked all kinds of questions about when the amount of sand is a maximum, how fast is the amount of sand changing. So we're going to practice here, and it's going to be the integral that we can use to help us answer all of these questions. So question A, pretty straightforward. You've probably seen something like this in your free response notebook already. How much sand will the tide remove from the beach during a 6-hour period? Well, the only thing that matters to this problem is how fast the sand is getting taken away and how long we stop and wait for sand to get taken away. So they were very specific. We've been told that we are interested in the time interval 0 to 6 hours. And we're going to integrate the rate at which sand is removed, and we've been told that is given by this function r of t. You could write out r of t if you'd like. You get just as many points on the AP test if you write r of t like I've done here. So 1 point for writing this integral and 1 point for, so you can see that I've typed this into my calculator. That's the integral from 0 to 6 of 2 plus 5 sine 4 pi x over 25. And the answer is 31.815 or 31.816 cubic yards. All right, so question B, this is the most important example from chapter 5. This got this little extra twist, because we don't just have how much sand was there at the beginning and how fast the sand is leaving. We also have how fast the sand is coming back in. So we are going to write an expression, y of t. That's going to equal the amount of sand we started with, 2,500, plus the integral from, we started at time 0, that's when we had our initial condition 0, to t. There's a couple ways you could do this. I'm going to write it with one integral, and then I'll show you how you could write it with two integrals. The amount of sand coming, the rate at which sand comes in is s of t. So sand is being added to the beach at the rate s of t, and the sand is being taken away at the rate r of t. So that could just go in big brackets here. Whoops! Look what mistake I made. That can be anything but t. Just pick your next favorite variable. So x minus r of x dx. So y of t is 2,500, the amount of sand that we started with, plus the integral from 0 to t of s of x minus r of x dx. Notice here at this subtraction sign, you could have split this up into a second integral. So you could have also written the integral from 0 to t of s of x minus dx minus the integral from 0 to t of r of x dx. Either one will get full credit. Okay, so question C is really interesting. Find the rate at which the total amount of sand on the beach is changing at time t equals 4. Now notice the things that are affecting how the amount of sand is changing are the rate at which the sand is leaving and the rate at which sand is coming in. It doesn't have anything to do with the 2,500 that we started with. That we could have started with no sand, or we could have started with a bajillion cubic yards of sand. But if we want to talk about how fast the amount of sand is changing, we have to examine how fast sand is coming in and how fast sand is going out. So two ways to think about this. If that, just thinking about it like that made sense to you, and I know some of you have already done problems in your free response book like this, it's totally correct. So the rate at which sand is coming in at time 4 is s of 4, and the rate at which sand is leaving at 4 is r of 4. So I can just compute S of 4 minus R of 4, which is, so I evaluated that on my calculator and I got negative 1.909 cubic yards. So yards cubed per units of time here are hours. If you had difficulty thinking through that the rate at which the amount of sand is changing is the rate at which it's coming in minus the rate at which it's going out, notice you have, in part B, a formula, a function that gives you the amount of sand on the beach. Well, the rate at which the amount of sand changes would be y prime. So let's go back and just for discussion, let's compute y prime. So y prime of t. So I'm going to take the derivative of 2500 with respect to t, which is 0. And then I'm going to take the derivative of this integral with respect to t. Well, it's an integral from 0 to t, so when I take the derivative with respect to t, I'm just going to have s of t minus r of t. So if y prime of t is s of t minus r of t, then y prime of 4, the rate at which the amount of sand is changing at time t equals 4 hours, is going to equal s of 4 minus r of 4. All right, so for part D, this is the exciting part. I know you've been waiting a long time to answer questions like these on your free response. So we've been asked to find out at what time the amount of sand is at a minimum, and then we've been asked to find how much sand is there at that time. So remember, this is an optimization problem. You see this, it's a superlative word. We have a minimum. So we're trying to, in this case, minimize this function that we've already written. We called it y of t. So we want to minimize y of t. I'm going to go to a blank screen. Okay, so what do? I make my table. In my table, I have t values. Those are the inputs to the y function. So I put my endpoints in. I also need to put in critical points of y. Well, what's a critical point of y? It's a place where y prime of t equals 0. Well, what is y prime? We just found it a second ago. It's s of t minus r of t. So we want s of t minus r of t to equal 0, and the time that that happens is when s of t equals r of t. So think about what this means. Here we're looking for where is the rate at which the amount of sand is changing? 0. Well, the amount of sand on the beach is not changing when the amount that's coming in is equal to the amount that's going out. So this is what I'm going to solve on my calculator. So here I've graphed R and I've graphed S, and I'm going to use the second calc and intersection function to find out their intersection point. Notice I'm only interested in intersections that lie on the interval 0 to 6. All right, so I found out that the two graphs, S and R, intersect at time 5.1178. I'm going to recommend that you keep more than 3 decimal places here, because when we see what's going to happen next, we're going to integrate with this time value, 5.1178, as an upper limit. And in order to get a result that's correct to 3 decimal places, we probably need our upper limit to be correct to even more than 3 decimal places. Okay, so now what's left to do is to fill in this column, the y column, with values I get by plugging these t values into y of t, which we wrote in part B, 2500 plus the integral from 0 to t of s of x minus r of x. Well, the easy one here is we know this is 2500. I'm going to calculate these two on my calculator and get back to you. All right, so now that I've filled in my table, I can see that the time at which the amount of sand is a minimum is that 5.1178 hours, and at that time there are 2,492.369 cubic yards of sand on the beach. So notice we've been asked to justify your answers. I'm going to write up my justification. I'm going to recommend highly that you write this down and you spend some time practicing it so that you can use it in your free response notebook too. So my justification has to include my reasoning for only including t equals 0, 6, and 5.1178 in my list. So to cover myself there, what I need to say is that candidates for the time at which the amount of sand on the beach is at a minimum are the endpoints t equals 0 and t equals 6, and any time when y prime of t equals 0. Notice that here I wrote y prime of t equals 0. Here I wrote s of t minus r of t equals 0. I also wrote s of t equals r of t. Any one of those equations would have been equivalent. So you could have written any one of them or all three of them. And then I have to justify why I choose... Oh, mercy. I hope you didn't see that. So, because I chose that time 5.117 hours, because at that time the y value is less than y of 0, and it's also less than y of 6. That's my final answer.